What's up guys, welcome back. In today's awesomely delicious, spectacular video, I'll be making a neural network from What do you mean that's already been done hundreds of times already? Oh. Huh, a convolutional neural network. Maybe that could be interesting. I mean, how hard can it be? Quick disclaimer before we start the video. I'm assuming you guys know what a neural network is pretty well, so all the terms here will not be explained further into the video. Okay, so to start off, let's try to quickly understand what a convolution is. There are many great videos about this online, but I know you're probably lying on your bed right now too lazy to click to another video, and I so happen to also need my retention rate to be higher, so you're in luck. So in simple terms, think of a convolution like a filter in Photoshop. Let's just take the blur filter for example. How it works is that it averages many pixel values of an area and uses that as a new pixel. Now you usually think of an average as summing up all the values then dividing by the number of pixels, but in this case let's just actually multiply each of these values by 1/9 and then sum them up. Now before someone in the comments ask, we retain the image dimensions by padding the edges with zeros. So if the area goes out of bounds, the value is just 0. Yes, it does make the edges slightly darker, but it lets us maintain our image dimension, which is a good trade. Anyways, we do this for every pixel in the image and voila, we have a blurred image. This is a convolution. Now let's get some key terms out of the way. The area that we apply across the image is called the kernel, and the dimensions of the kernel make up our kernel size. Now the values that we multiply by are called our weights, and they don't have to all be 1/9. They can be even larger than 1 and negative. Now this is great, but how does this have anything to do with machine learning? Well, in a convolutional neural network, our aim is to find the kernels that when applied over our image can extract certain features. So for example, maybe our model will find a kernel that would look like this, and when it's applied over our images here, notice how the cross section of the X gets highlighted, which the model can later use to classify these images. Now I'm leaving out two details. Firstly, there's a bias applied, but that's pretty boring, so I won't talk about it for the rest of the video. You're welcome. Secondly, our kernels are actually 3-dimensional. And to reference this third dimension, I use the word channel or layer interchangeably. Going back to our blurred image, notice that it's not just a single value for each pixel, but rather an R, G, and B value. So instead of a 2D image, we actually have a 3D image with 3 layers that holds the individual RGB values. And instead of a 2D kernel, we have a 3D kernel with 3 layers, all with individual weights. Note that all of the values are still summed together, so after applying our kernel, we collapse our 3D image into a single layer. This has the side effect of turning our image grayscale, so if we still wanted to represent a blur with color with our network, we would have 3 separate 3D kernels that would have zeros in channels that aren't theirs. That way, each kernel only considers its own color channel. This may seem quite convoluted, but later it'll make more sense when we generalize it. Okay, hopefully now that you got the Hey, don't click away yet. Here. Now let's understand how the network works through this example. So we start off with a 14x14 image, and I originally wanted to do MNIST, which is 28x28, but my computer quickly told me that that's not happening. Anyways, then we have 8 kernels that are dimension 2x2x1, and each of these kernels build their own layer in the new image. Note that in addition to the bias, we perform a ReLU on the outputs, so that's why everything here is positive. Now since we apply 8 kernels, our new image has a dimension of 14x14x8. And I don't really know what it would mean for an image to have 8 separate channels, so I choose to think of each channel as extracting certain features of the image, like the X from earlier. Anyways, this is a lot of information, so to try to keep only the important stuff, we divide the image into grids of 2x2 and take the maximum to form the new image. By doing this, we are essentially shrinking the X and Y while keeping the number of channels. This step is called max pooling and is distinct from applying our kernel. Anyways, what we're left with is an image of size 7x7x8. And now the secret sauce is to apply another convolution on the new image that has 8 channels. Note again that even though the kernel has 8 channels, it collapses the image down into a single dimension. Since we have 16 kernels though, this creates an image of dimension 7x7x16, and I choose not to pool here since we're already working on a downsample of MNIST. Anyways, we can do this as many times as we want, but I decide to just do it one more time with 8 kernels, So apply them, new image size, pool it, and what we're left with is an image of size 4x4x8, which hopefully extracted all the important details from the image. We then flatten this out and have a neural network refine it into our different classes. This neural network is called the fully connected layer of the model because, everything's connected. Great, since now that you understand, what's this still doing here? I mean, if you're still here, you probably didn't need it, right? Yeah, that's what I thought. Anyways, let's get into the real meat of the video, which is all the math behind the convolution. And this is where we actually run into our first fundamental issue, which is that it's very computationally intensive. The model that I just showed you was a scaled down version of the model that I actually used, but even here, think about it. We have 16 kernels with dimension 2x2x8 that we have to apply over a 7x7x8 image, and that's only for a single layer. The real network that I use takes about 350 million floating point operations to complete. Wrap your head around that. One image takes 1/3 of a billion multiplications or additions. And this is not a training cycle. I haven't even talked about the math behind training yet, but that adds around another 750 million operations. So to train a model with one image, it would take 1 billion operations. And this provides you with 42,000 images, so that's 42 trillion operations to train a single epoch. My CPU runs at 2 GHz, meaning that with perfect code, it would take 350 hours to train. That's almost as bad as my upload schedule. So instead, let's use Jensen Huang's favorite bargaining chip, the GPU. I have a pretty decent GPU that can perform 29 trillion operations per second, so instead of 350 hours, it would actually take 2 seconds. In reality, perfect code like this doesn't exist, but hopefully you can understand why GPUs are used in machine learning. Anyways, I went on a bit of a rant about using the GPU, but the reason this is important is because the way you program on a GPU is very different than on the CPU. Many people know that GPUs have many cores that run in parallel, but far fewer people know that these cores are not independent. Instead, they run in work groups which share memory and resources. So to efficiently program on the GPU, you would have to make use of these work groups to share memory loading and usage. What do I mean by this? Let's use a simple example of our neural net. Imagine if we treated each thread independently so we don't use work groups efficiently. We assign each output neuron to a single thread and load in all the inputs from the previous layer and then load in all the weights for each input. Then we pause. See the problem? We have to repeatedly read the same input layer multiple times for all our cores, resulting in a bandwidth bottleneck. This is a small model, so the impact doesn't seem that severe, and even for massive neural nets we can work around this. But if we move to convolutions, we're suddenly dealing with billions of operations and memory accesses, which creates a non-negligible bottleneck in our system. So how do we solve this? The answer is with matrices. Let's forget about neural networks for a second and just try to multiply these two matrices together using a GPU. And just for those who forgot how matrix multiplication works, here's an animation. Now the numbers can be quite messy, so instead I'm going to simplify them to squares. Anyways, this should be quite easy. We can assign each output to a thread and then read this row and that row, and once we do this for every output, wait, but isn't this the same? I know most of you are sleeping right now, but to those that are still paying attention, yeah, this is the exact same as the previous algorithm, so the same bottleneck. Instead, what we do is assign each work group a tile of the output matrix. Now, each thread still writes to a single output, but now instead of performing a matrix multiplication on the whole matrix, we perform a smaller multiplication on these two input tiles. And the way that this is arranged, each thread can help read and add 2 values to a buffer in the workgroup that's shared between the threads. By sharing data reads between threads, we can reduce the number of total data reads from VRAM that we need. And when the threads perform their matrix multiplication, they read from this workgroup buffer where memory reads are much cheaper. And then to get the multiplication of the whole matrix, we iteratively shift the input tile and perform the same algorithm to get the multiplication of these two new input tiles. Note that this doesn't actually decrease the number of operations done by each core, it just caches the values so that operations can be done faster. Anyways, we increment our previous values by our new outputs, and we do this until we read all the values of our matrix. With multiple workgroups working in parallel, this speeds up our compute time by a lot. And with just a neural net, it helps speed up the computation from 1 millisecond to 0.2 milliseconds, or 500% faster. Oh wait, I should probably explain how this matrix has anything to do with our neural network. So looking back at how we perform a forward step with a network, you notice that it looks awfully similar to what we do in a matrix multiplication. So it begs the question, can we represent a forward step in a neural network with a matrix multiplication? And the answer is a resounding yes. So using some simple intuition, you get a matrix with all the weights here and multiply it by a matrix with all the inputs here. Well, I mean, if you can call this a matrix. And this is actually a problem because if you remember how we make use of our workgroups efficiently, it takes a square tile. Thankfully, we can solve this quite easily by bringing batching into our multiplication. So instead of only having one input, we can take the inputs from multiple batches to add an extra dimension to our matrix. And after you carry out the multiplication, you get the inputs for the next layer arranged very nicely. Now let's take a quick refresher to remember how backpropagation works in a neural network, since we'll be using this concept later for convolutions. This will be just a quick summary, and there will be many assumptions that aren't explained fully, so if you want more information, go watch 3 Blue 1 Brown's video. But anyways, here's an example model. Since we want to find out how much each weight affects the loss, we can see that this weight directly affects this output neuron, which affects these final outputs through these weights here, which finally decides the error. So if we know how much this weight affects this output, and how much this output affects the final outputs, and how much these final outputs affect the error, we can essentially multiply them together to find out how much this weight affects the error. Now, the part that I want to show is that to find out how much this weight affects the error, we would just multiply it by its output derivative and the input. And to find out how much this output affects the error, we would just sum up the weights multiplied by their output derivative. If you want more information, again, go check out 3 Blue 1 Brown's video, but the main idea is it kind of makes a sort of triangle in a sense, where the derivative of one corner of the triangle is associated with the sum or multiplication of the two other related components. Anyways, moving back to matrix multiplication, it turns out that you can do this operation for backpropagation too. So to calculate the input gradients, remember we want an operation with the weights and the output derivative, so we can have a matrix multiplication that looks like this. And to calculate the weight gradients, remember we want an operation with the inputs and the output derivatives, so we have a matrix multiplication that looks like this. Quick side note, since we have batching, the matrix multiplication automatically sums up the gradients for each batch, which is quite a nice feature. Oh, you have no idea how much animating that was. But anyways, now that we have all of this, we can finally train a model. I trained the model on MNIST with each epoch taking around 0.5 seconds for 42,000 values and got an accuracy of around 90%. Not great, but not that terrible either. Now let's move to a harder dataset that I haven't seen that many people use, and that's MNIST letters. This is much harder than MNIST since letters are generally harder shapes to recognize, and there's 26 categories compared to only 10. Additionally, the model will have to recognize 2 different versions of each alphabet, and capital letters are also included. Training the model again, I got 81% accuracy, which is honestly a lot higher than I thought. Okay, now let's go back to the main focus of the video, which is our convolutional neural network. Let's start off with the forward prop. We mentioned that we need to keep everything in a matrix in order to make computation efficient, but is that even possible? Well, it turns out once again that it is, but it's not as pretty as last time. Since now we're convolving over an image, the same pixel gets read multiple times through our convolution. But you'd notice that the basic idea remains of multiplying 2 unique values together and then summing them up. And you would also notice that each kernel reads the same values. So what we can do is flatten a single convolution into a line, and then similarly flatten the kernel into a line. By taking the matrix multiplication of these 2 lines, which is really just the dot product, we're essentially doing our convolution. Then we can take every possible convolution of our image, flatten them into another line, and now you can see that multiplying this matrix by our kernel is the same as taking the convolution of the image. Note that I'm doing this in 2D, but the same idea can be transferred into 3D. We then flatten all our kernels and line them up, and once you do all of this, you can actually represent the whole convolution operation of a single layer with a matrix multiplication. Now, there's one caveat to this again, which is that we lose our batching. So to get our batches back, we have to artificially add more lines into our matrix, and this is kind of goofy, but I won't mention it for the rest of the operations. And actually, this is the last matrix multiplication that I'll explain, not because we don't use matrix multiplications anymore, but because it's the last important matrix concept. So celebrate while you can, people. Now, I have bad news for you. Everything before this was child's play because you are only now entering the hard part, which is backwards propagation of a convolution. Notice that in a neural network, the inputs and outputs are very organizedly laid out, which makes animation easy, but more importantly, makes it really easy to highlight and point at what affects what. But in a convolution, we kind of have to imagine the kernel scanning across the image, so it's a bit harder to conceptualize what's happening. Also, the pipeline is different. When we're in a neural net, notice that we're just trying to calculate the outputs of the next layer. So then the backpropagation pipeline looks like this. But in a convolution, our forward prop has 2 distinct steps. which is our actual convolution, and pooling. And while this is happening in the background, notice that I'm simplifying it into 2D by only having one kernel, but in a true convolution we have multiple kernels, so this process does happen in 3D. So now our backpropagation pipeline looks like this. So now we have 4 parts to cover, which is how we get our final output derivatives, how we get our weight gradients, how we get our input derivatives, and how we unpool our derivatives. The most important thing that will get you through this is this triangle. You don't have to memorize it since I'll be so kindly putting it into the corner of the screen, but make sure you don't forget the idea of how these 3 corners are related. Now let's start off with the easy parts, which is our final outputs and pooling. So for the final output layer, we're at the transition of the neural network, so we can calculate the input derivatives for the neural network and then just unflatten them back into the final layer of the convolution. Next, for max pooling, let me just quickly show you how this works again. So intuitively, you can see that since only these values actually affect the rest of the convolution, once we get the output derivatives of this layer, we can just transfer it back into the spots which were pooled and set the other input derivatives to 0. Pretty simple. Okay, now the hard parts, which is our weight gradients and our input gradients. Now let's start off with the weight gradients. Looking back at the triangle, we need to find the corresponding output derivatives and inputs. So I'm going to focus on this weight when convolving the image and separate the output derivatives and inputs that it interacts with into a line. Note that from this, we can actually already calculate each weight gradient by summing up the multiplication of each pair, similarly to what we did in a neural network. But this fact alone is quite useless unless we know some pattern to get these pairs quickly without having to slowly go through our convolution and mark each one down. So let me color code them and then put them back. Doesn't that look quite similar? No? Well, let me line them up in this fashion then. How about now? It's almost like the weight gradients are some convolution of the input and output derivative, and it turns out this is exactly what it is. But instead of taking the convolution of the inputs with the kernel, we take a convolution of the outputs with the inputs. And when I select different weights, notice how the convolution changes. And we can actually derive the gradients of our convolution this way. Now the matrix math is exactly the same as the convolution, so I won't explain it, but I do have to show it because there's something that we need to discuss. Notice that although the dimensions of the output matrix are quite small, the size of the input matrices are enormous. And this is because we have a super big kernel, since our kernel is now the size of the entire output layer and the input layer. So even with our efficient matrix multiplication, a single core would still have to multiply all these values together. So what I do is I split up the single large matrix multiplication into separate smaller multiplications, which lets me utilize more cores of my GPU and decrease the workload on a single core. Now let's go through our input gradients. Looking at this triangle again, we need to look at the output derivatives and the weights. And now that we have this, let's focus on this input and let me separate the pairs again. Color code them, and then put them back. Well, this looks like we have another convolution. But now note that our pairs don't exactly line up, so we can't just do our convolution as it is. Thankfully, there's a pretty cool trick to solve this. If we rotate our weights by 180 degrees, notice that they're once again lined up. So we can use a convolution that looks like this to get the weight gradients. This is what the matrix math looks like again, but thankfully this time it's actually a manageable size, so no fancy tricks needed. I don't know if anyone actually followed any of that, but congratulations. If you did, you just learned the math behind most computer vision models. Now let's retrain the model on MNIST, and now each epoch is taking about 3.5 seconds, but I got an accuracy of 99%. Going to MNIST letters, the model now takes around 8 to 9 seconds per epoch, but notice that I'm running this at about 14,000 gigaflops per second, which is about 40% of my max GPU capacity, which I'm insanely proud about. Anyways, that has no meaning unless I get a good accuracy, and I get an accuracy of 90%. Honestly, I wish it would be higher for all the work that I did, but I'll take what I get. Now, before I end off the video, here are some things that I need to improve on. Also, in the background, I'll be flipping through the notebook that I used during these 4 months to prove that I actually went through the suffering and did this legit. Firstly, I practically learned how to use the GPU when making the neural network portion, which honestly I'm quite amazed I even got as far as I did, but more importantly, the code there is complete dog shit. So if I continue the project, that's the first thing I'm fixing. Secondly, I originally wanted this video to have a practical application, which I will keep a surprise if I choose to do a second video. But the problem is that A, my network crashes with large buffers, so I need to find a workaround with that. And B, I need to implement strides for the kernel so that the input and output layers are smaller and my GPU won't explode. But I just wanted to upload something to show something so that YouTube won't get mad at me. Lastly, before I end off, every minute of this video was 2.5 hours of animating and editing, not even including the coding, so it would mean a lot if you subscribed, liked, or just shared the video. Anyways, thanks for watching and see you next time.